You can store billions of facts, but without a mechanism for snapping them together to derive new truths, it is just a very large encyclopedia. Moving from data storage to artificial intelligence requires knowledge representation, or KR. In symbolic AI, KR is a formal language designed explicitly for machine execution. To be useful, this representation must achieve inferential adequacy, the mathematical ability for an algorithm to manipulate existing facts to automatically produce new ones. We can see this structure in a classic rule-based system architecture. This block diagram maps out three core components. While a database remains static, an inference engine enables the system to calculate its own results. This shift from manual lookup to autonomous derivation is the functional transition from simple storage to a reasoning system. At the bottom, the knowledge base stores strict if-then rules. Up top, the working memory is a scratchpad holding known facts and intermediate results. Between them sits the inference engine, a semantic reasoner matching temporary facts against permanent rules. This is entirely different from running a standard database search. A search retrieves what is already there. An inference engine calculates what must be true based on the surrounding logic. To understand how this active calculation works, we have to deconstruct how the inference engine mathematically traverses these structures and resolves syntactic contradictions. Here we see how production rules are translated into a directed acyclic graph for the machine to traverse. On the left, we have raw logical implications, and on the right, their geometric equivalents. A direct implication creates a straight path from one node to another. But when a rule requires multiple conditions to be met, the graph uses an AND gate, forcing the system to confirm several paths before moving forward. When the system navigates this graph from the bottom up, it uses a data-driven strategy called forward chaining. Look at the bottom of this diagram. Nodes A and B are marked with a 1, meaning they are verified facts currently sitting in working memory. Because both A and B are true, they satisfy the first rule's AND gate. This pushes the logic up to the next level, generating a new fact at node L. This new truth cascades. The activation of L, combined with other confirmed facts, triggers the next sequence of gates, driving the logic all the way up to node P. In this process, the engine fires every possible rule whose premises are met, generating new data until no further rules apply. While this exhaustive method ensures every possible conclusion is mapped, it carries a high computational cost. If you only need to answer a single specific question, calculating every implication of every fact wastes processing power. To solve this problem, systems deploy the exact inverse strategy, backward chaining. This is a goal-driven, top-down inquiry. Notice the green node Q at the top of this graph. Instead of starting with raw data, the engine begins with the specific query it wants to prove. From there, the algorithm searches downward, looking for the immediate prerequisites required to satisfy that primary goal. If Q requires P, it asks, what does P require? By working backward through P, M, and L, the system isolates the exact foundational facts it needs, in this case, nodes A and B. Finally, the algorithm checks working memory. If those specific subgoals match the known facts, the initial query is definitively proven. Backward chaining reduces computational overhead because it selectively ignores any rules or facts in the knowledge base that do not directly support the query at hand. Graphical chaining works for direct rules, but it fails when dealing with complex nested statements or logical negations. Graphing the absence of a fact breaks the visual geometry. For these complex scenarios, the system uses the resolution algorithm, a universal automated theorem proving rule that bypasses graphical logic entirely. To run resolution, the machine translates rules into a flattened structure called conjunctive normal form, or CNF. Let's look at this formula. Step 1 removes the biconditional operator. The algorithm splits the equation into two directional implications linked by an AND operator. Step 2 eliminates the implication arrows. It replaces the arrows with OR operators and negates the premise of each side. Next, the system applies De Morgan's laws. It pushes that negation inward, flipping the inner OR to an AND. Finally, applying the distributive law flattens the entire structure into a uniform sequence, a conjunction of disjunctions. This is pure CNF. With the knowledge base standardized, the resolution algorithm performs a proof by contradiction. It takes the exact opposite of the target query and adds it directly into this newly slattened fact list. The algorithm then scans for complementary literals, an A and a not A, and recursively cancels them out, merging the remainders. It repeats this until the clauses collapse into an empty set. Resolution proves truths by mathematically demonstrating that assuming the opposite of the goal results in a syntactic contradiction. Whether an inference engine traces a directed graph or computes syntactic resolution, it is executing strict deterministic mathematics. But the propositional logic we've looked at has a serious limitation. It lacks internal sentence structure, reducing complex, real-world concepts down to indivisible, singular symbols like P or Q. This means a machine can evaluate a statement like Ram is a student as a single, isolated truth, but it cannot apply generalized rules to the abstract concept of all students. To solve this, AI requires first-order predicate logic. This is an expanded language that defines objects, their properties, and the relationships between them. Notice how the predicate formula on the right introduces specific variables instead of opaque symbols. It introduces the universal quantifier, the upside-down A, allowing the system to declare truths about entire classes of objects simultaneously. It also uses the existential quantifier, a backward E, to mathematically declare the presence of at least one specific instance of a property within a set. Propositional logic forces the machine to process rigid, isolated true or false statements. Predicate logic gives the machine an object-oriented syntax to group, classify, and relate concepts. Rule-based architectures provide the mechanical engine, but predicate logic provides the necessary vocabulary, the quantifiers and objects, allowing AI to map the structures of the real world.